Welcome back, engineers. Today we are tackling massive payloads by mastering parallel execution. We will deep dive into the fan-out and fan-in, or MapReduce, pattern to bypass context limits and slash latency. Let's get started. As senior developers, we constantly face the limits of LLM context windows and latency. When processing a massive document or a long video, feeding it all at once is slow, expensive, and error-prone due to the model forgetting middle context. Enter the MapReduce pattern, or fan-out and fan-in. We fan out, or map, by splitting the large input into smaller, independent chunks and sending them to the LLM simultaneously. Then we fan in, or reduce, by taking those individual responses and combining them into one final, coherent output. This parallel execution drastically cuts down processing time and allows us to bypass strict token limits securely. Look at this architecture flow. A massive input enters the system. Instead of a single bottleneck, the router node splits the payload. This is the fan-out or map phase, launching parallel worker nodes simultaneously. Finally, their isolated outputs converge at the reducer node. This is the fan-in phase, yielding our final, synthesized result. Let us zoom in on the map phase. To fan out effectively, we must first chunk our data intelligently. If we're analyzing a video, we split it into clean 10-minute segments. The critical architectural challenge here is dynamic scheduling. In enterprise systems, we often do not know the exact number of chunks until runtime. Modern orchestration frameworks, like LangGraph, handle this by allowing us to dynamically schedule parallel node executions based on the array of data. Each parallel worker receives its specific chunk and a shared system instruction, executing completely independently without waiting for its siblings. This shifts our time complexity from linear to constant. Here is the map phase isolated. The global state holds our chunked data array. The system dynamically spins up multiple map worker nodes based on the array size. Each worker operates in complete isolation, communicating only with its assigned LLM instance to produce a specific chunk result, guaranteeing true parallel execution. Once our parallel workers finish, we enter the reduce phase. The framework collects the isolated outputs, say, individual summaries of our video chunks, and safely merges them back into the main state array. Our reducer node then activates. It takes this aggregated list of intermediate results and feeds them into a final synthesis prompt. Because the heavy lifting of reading the raw data was done in parallel during the map phase, the reducer's job is highly efficient. It simply stitches the narrative together, ensuring consistency and resolving any contradictions between the chunks to deliver a polished final report. Observe the data convergence in this diagram. The intermediate summaries flow from the parallel workers into a unified state reducer array. The final LLM synthesizer node consumes this entire array in one prompt, synthesizing the fragmented data into a single cohesive final report. How do we actually build this? In LangGraph, we use the send API for dynamic routing. When we define our conditional edge, instead of returning a single node name string, our router function returns a list comprehension of send objects. Each send object specifies the target node, our map worker, and the exact payload or substate it needs to process. This tells the LangGraph execution engine to spin up parallel instances of that node, one for each payload in the list. It is a highly elegant, Pythonic way to orchestrate fan-out dynamically without ever hard-coding the number of parallel branches. This sequence illustrates the dynamic routing mechanism. The router function evaluates the data array. Instead of a single path, it yields a list of multiple send commands to the LangGraph engine. The engine intercepts these commands and dynamically instantiates the exact number of parallel map nodes required, executing them simultaneously. Let us look at the code patterns. To manage this safely, we need two states, an agent state for the main graph and a chunk state for the individual map tasks. In our agent state, we define a variable like summaries and use the annotated type hint with Python's operator .addReducer. This is absolute critical architecture. As each parallel map node finishes asynchronously, it returns a summary string. The operator .addReducer guarantees these parallel outputs are safely appended to our global list without race conditions or overriding each other. The global state remains pristine, ready for the final reduce function to process the complete array. This class diagram maps our data structures. The main agent state tracks the global data and the summaries array, strictly equipped with the operator .addReducer. The chunk state is the localized payload spawned via the send API for each map worker, completely decoupled from the global state. When finished, it merges its results back up using the add operation. Let's apply this to a highly impactful use case, summarizing a Tower corporate all-hands meeting. If we feed a Tower transcript directly into an LLM, we hit the token context limit, or the model suffers from lost in the middle syndrome, forgetting key decisions made at minute 45. The latency would also be unacceptable. Using MapReduce, we slice the video transcript into 12 10-minute chunks. We fan out to 12 parallel agents using the Send API, each summarizing their specific 10 minutes simultaneously. Finally, we fan in, passing the 12 concise summaries to an executive reducer agent that writes the final boardroom report. This drops our processing time from minutes to seconds, with zero lost facts. Follow the data flow for our meeting summary. The massive 2-hour transcript file is sliced into 12 distinct chunks. These flow into 12 parallel agents simultaneously via the Send API. Their outputs append into the summaries array, which converges into the executive reducer. The framework synthesizes the comprehensive final executive report in a fraction of traditional processing time. While MapReduce is incredibly powerful, we must engineer around the trade-offs. Parallel execution drastically reduces latency, shifting time complexity from linear to near constant. However, fanning out aggressively to 50 chunks simultaneously will spike your API token usage and trigger 429 rate limits from your LLM provider. The enterprise fix is utilizing concurrency controls such as setting max concurrency to 5 during your graph invocation to batch the parallelization safely. When configured correctly, this pattern is unmatched for scaling AI over infinite context. I invite you to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Master these architectures and elevate your AI engineering career. Our final chart shows the architectural trade-off. The bars represent latency, while the line represents API request volume. Sequential processing has terrible latency but low request volume. As we increase concurrency, latency drops beautifully to 15 seconds. However, the far right warns us, extreme concurrency triggers the rate limit zone. Balancing these forces is the mark of a senior architect.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by Quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material. So this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see these are all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all the practice papers are available here. Today we have 5 practice paper. So click on the first practice paper. It would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepared for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.